In this video, I want to have a look at similar triangles. So more generally first, two figures are similar if they have the same shape but not necessarily the same size. So one of the figures is either an enlargement or a reduction of the other figure. The symbol that we use for similarity is this here, so three vertical lines. Now if we have figures that are similar, that means that their corresponding or their matching angles are equal and their corresponding sides are in proportion. So that means, for example, if one side length had tripled in length, then all the other side lengths must have tripled in length as well. If we have a little bit of a closer look at that proportion or that ratio, like we said, if our similar figures have a ratio of 1 to k, so for example, 1 to 2, that would mean that every side length in the first shape had doubled in the second shape. So the side lengths have that same ratio. But if we look at the area of our figures, then they're going to be in the ratio of 1 to k squared. So if we use this example again, that would be 1 to 4. So that means any area in the first shape would be multiplied by 4 in the second shape. And if we look at that last one, it says corresponding solids have the same volume, have volumes in the ratio of 1 to k cubed. So ours would be in the ratio of 1 to 8. So the volume of the second figure is 8 times the volume in the first figure. If we look specifically at triangles now, we've got 4 tests to prove that two triangles are similar. The first one is called the SSS test, or side, 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 and it says that all 3 pairs of corresponding sides are in proportion. So if we have a look and match up our sides here, we can see that DE matches AB. So we could write that as DE over AB, and that would be 18 over 9, which would give us 2. So we can see that this side here has been doubled to get this one. If we did the same thing with all the other matching sides, the 5 has been doubled to get the 10, and the 10 here has been doubled to get the 20. So because all 3 of those pairs are in that same ratio, that means that they are similar triangles. The second test is called the SAS test, and that's side angle side, and it says 2 pairs of corresponding sides are in proportion and the included angle is equal. So in this example that we've got here, we've got 40 degrees as the included angle in both of these triangles. And then if we match our sides up, we've got a 6 and a 2, so that's a ratio of a third. And then we've got 9 and 3, which is also a ratio of a third. So because they're in proportion and our included angles equal, those two are similar. The third test is what's called the AAA test, or angle, 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 which says that 3 pairs of corresponding angles are equal. Now we've also written it like this here because in a triangle, if we know that 2 of the angles are equal, then because of the angle sum of a triangle, the third angle must be equal as well. So when we're writing up a proof that involves this test, we actually only need to prove that 2 of the angles are equal to each other because the third one then has to be. So in our example, both of these triangles have the 50 degrees here. We've got 100 degrees. So that would be enough for our proof. And that's because 150 gives us 150, which means that this angle up here would have to be 30 in both of those. So all 3 angles are equal. The last test is called the RHS test, which tells us that both triangles have a right angle, which in our example they do down here. It tells us their hypotenuses are in proportion and one other pair of corresponding sides is in proportion as well. So if we look at our hypotenuses, we've got a 4 and a 16, so that's a ratio of 1/4. And we've got a 3 and 12 matching up as well on those corresponding sides, which is that same proportion of 1/4. So if we have a look at our first example, it says the diagram below shows 2 concentric circles with centre O. Part A asks us to prove that triangle ABO, so ABO, is similar to triangle CDO. And then we'll have a look at part B in a minute. So for part A, the first thing I notice is that because they're 2 circles with centre O, that means that this side has to be equal to this side because they're both radii of the same circle. And also that this side BO and AO have to be equal in length as well because they're radii of the big circle. So I'm going to write this down first. So we'll start off with in triangle ABO and triangle CDO. We know that CO has to equal DO, and our reason is equal radii. And we also know that AO has to be equal to BO for that same reason. What that means then is that the ratio of our corresponding sides, so CO over AO, has to be equal to the ratio of the other two corresponding sides, DO and BO. And that's because CO and DO are equal and AO and BO are equal. So that means that those two ratios are going to be equal, those two fractions. So that means that we've got two pairs of corresponding sides in proportion. The other thing we need to prove this is similar is the included angle. So we also know that this angle here has to be equal to this angle here because they're vertically opposite. So we can write angle AOB equal to angle COD, vertically opposite. So that means, like I said, we've got our two sides in proportion and we've got our included angle. So that's going to be, they're similar because of the SAS test. Okay, so that's part A. Part B says then that given OA is 8 centimetres, so let's write this on. That's 8 centimetres there. OD is 6 centimetres. And also AB is 12 centimetres. Then we want to find the length of CD. So CD is this one along here. So that one there, this side here, matches up or corresponds to the side AB. And the side AO and DO are corresponding as well. Now you could match AO up with DO or CO. It doesn't matter which way you do it. So what that means for part B is that they have to be in the same proportions. So that side CD divided by AB has to be equal. If we went the small triangle to the big triangle, so we have to do it in the same way. So that would be our DO over AO. So if we fill in the numbers that we know, we're going to have CD over 12 is equal to 6 over 8. I'm going to move over here a little bit because I'm running out of room. So that means to find CD then, we're going to go 12 times, 6 over 8 simplifies to 3 over 4. 12 divided by 4 is 3, and then 3 times 3 would give us 9. So that means CD has to be 9 centimetres. Our second example asks us to prove that triangle ABC, so this small one up the top, is similar to triangle ADE, so still starting at that top point and coming into the big triangle. Then it says, and hence find the value of X, so the length of this base here. So looking to prove that these are similar, we don't have enough information about the side lengths to tell us whether or not they're in proportion, but what we do have is information about the angles in our triangle. So this angle here, this angle A, is part of both of our triangles. So that means that angle A is common or shared. The other thing we have in there is parallel lines. So BC is parallel to DE. And that means that we can tell that this angle here is equal to this angle here because they're corresponding angles in parallel lines. We could also have done that this angle here was equal to this one for the same reason, but we don't need to prove all three things. We only need to prove two of those facts. All right, so let's start off. So we've got in triangle ABC and triangle ADE. We've got angle A is common. We've got angle ABC is equal to angle ADE. And the reason is corresponding. So corresponding angles, and then we need to write our parallel sides as well, which is BC parallel to DE. So we've got our two angles, which then means that a third one has to be equal as well, but we don't need to show that. So therefore, triangle ABC is similar to triangle ADE. And our reason is the AAA test, or you can write AA and then an arrow. So that's proof that they're similar. The next thing asks us to find the value of X, so find the value of this side here. Now to do that, I'm actually going to draw our two triangles separately. So if I draw a triangle ABC, that's BAC, we've got this side here being 4.2 and this base being 5. So that's just our top little triangle. If I draw our big triangle now, so that's ADE, that base is X, that's what we're trying to find. And we also need this side AE because it's the corresponding side to that 4.2 that we've already been given. So AE is going to be our 4.2 plus our 6.3, which would be 10.5. So if we then go and match up our corresponding sides, we're going to have X over 5, because that's its corresponding side, is going to be equal to, we need to make sure we do our triangles in the same order. So we had X on the top, so we need to have our 10.5 on the top, over its corresponding side, which is 4.2. So then to find our X, we need to get rid of that 5, so we're going to multiply both sides by 5. So we're going to have X equals 5 times 10.5 over 4.2, which will give us 12.5 centimetres. So that's a look at similar triangle proofs.